In this video, we will explain the notion of differential equation. Maybe before doing that, let me remind you about regular equations. Like if you have like the equation x squared minus 4 equals 0, and let's suppose that we are looking for a real number. X is a real number. We have a variable which is x, and usually when you have a variable and you're looking for an equation, we have the range of the variable. In this case, the range of the variable, it tells us what should we try to replace that x for. And in this case, it says try to replace x with any real number. And if we have something like this, then the equation, the solution, we know that the solution is x equal 2 or x equal negative 2. Out of all possible real numbers, these are the two that satisfies that equation. When we have a differential equation, that we have a variable, let's suppose that we are looking only for one function. And in this case, we call this variable y, but y is a function in terms of t. And we're going to be using t as the independent variable. And notice that in our equation, the range of the variable is the set of functions. This is just set of functions. It's a set that is a lot more larger than the set of real numbers. Even when we have when we write y equals 2, this doesn't mean y is equal to number 2. It means y is the constant function 2, right? Y equals 2. When we have a differential equation, we are always looking for a function. But not every time that we are looking for a function, we have a differential equation. For example, if we have y plus sine of t equals t, then here we're looking for a function and we can easily solve this. This is t minus sine of t. And we can say, we solved the differential equation. No, this is not the case, because the other condition to have a differential equation is that at least one derivative of y should be present in the differential equation. Then let me write that definition. We just say that, let me write it here, maybe definition. An ODE, and this is going to refer to ordinary differential equation. It's an equation that searches for a function as a solution, and it involves at least one of the derivatives of the function. If the highest derivative in the equation is the derivative of n of y with respect to t to the n, then we say that it is an order n ordinary differential equation. Let's see some examples. If we have like dy dt plus 2y equals 14e to the t, notice that here the y is a function, there is a derivative, then this equation classifies as an ordinary differential equation, and the highest derivative that we have here is a first derivative, then this is an order 1 ordinary differential equation. If we have an equation like d3 of y with respect to t, q times dy dt plus 2t equal to 4y, then this is an example of an order 3 ordinary differential equation. Okay, in the same way that when we have an equation, let's suppose that we have the equation x to the 5th minus 3x plus 4 equals 0. This equation may be difficult to solve, but something that we can easily do is to check, if we're looking for a number, is to check if a number is a solution or not. Let's suppose that we want to check if x equals -1 is a solution of that equation. Then we do what the equation tells us to do. The equation is telling us raise to the power of 5. Then we have -1 minus 3 times -1 plus 4. And then we just need to check if this is equal to 0 or not. In this case, it is not. That means that this is not a solution. When we have a differential equation, we can do the same. To solve a differential equation sometimes is extremely difficult, sometimes it is impossible, but then to check if something is a solution or not is something that is relatively easy. Let's see some examples. Let's suppose that we want to check if the function 3 cosine of t is a solution of this differential equation dy dt equal to y plus sine of t. How do we do that? We need to do what the differential equation tells us to do, something similar to what we did here. Then we compute the derivative. What is the derivative of 3 cosine of t? It is -3 sine of t, and the question is this function equal to the function y? But what is y? It's 3 cosine of t plus sine of t. These two functions are different. For example, when t equals 0, we have that the left-hand side is 0 and the right-hand side is 3. Remember that the difficulty of a differential equation is that we want two functions to be the same. That means that a differential equation somehow is a collection of infinitely many equations that we want to fulfill, one for every t. We want that for every t, the part on the left is equal to the part on the right. Let's do another example. What about if we want to check if y equal to 3e to the 2t, check if this is a solution of the differential equation dy dt equal y plus 3 times e to the 2t. Let's see, we do what the differential equation tells us to do. Then it says take the derivative. The derivative of this function is 6 times e to the 2t, and we want to check if this is equal to y, but y is 3 e to the 2t plus 3 e to the 2t. Are these two functions the same? Yes, they are. That means that this function is a solution for this differential equation. We will see that there are infinitely many solutions, but this is one of them. Let's see another. Let's see if y equal t squared is a differential equation of this is a solution of this differential equation 2y over t. We have that. Let's see if we take the derivative, we have 2t, and here we have 2 times y. 2 times y is t squared and divided by t, and we notice that they are the same, 2t equal to t. An observation about this example is that this is a solution, but we have to take either t bigger than 0, because t is not allowed to be 0 in this differential equation, or we can take t smaller than 0. We usually consider solutions of differential equations defined only on one interval. Let's do another example. Let's suppose that we want to check if we can, this is the question, can we find a number, such that y equal to a e to the t is a solution of the differential equation dy dt equal to 2y plus e to the 4t. How do we solve this problem? Can we find an a such that that is true? Okay, what do we want to do? We want to, for any a, we want to check if this is a solution of this. Then we do what the differential equation tells us to do. Then the derivative of this function is a e to the t, and then we want to see if this is equal to 2 times y, 2 times, but y is a e to the t plus e to the 4t, and therefore if such an a exists, then we must have that a e to the t plus e to the 4t is equal to the constant function 0. But we see that this function, it doesn't matter what a is never the function 0. That means that this a does not exist. What about if we have the same differential equation, but now we look for something of the form e to the 4t? Then in this case, when we take the derivative, we get 4a e to the 4t equal to 2 times a e to the 4t plus e to the 4t. The idea is to see if we can find an a such that this function is a solution. But then we can move this to a here, and we have 2a e to the 4t equal to e to the 4t. Can we find an a such that these two functions are the same for every t? And the answer is yes. If we pick a equal to 1/2, then we have that this function is a solution for this differential equation. Then the point is that we can easily check if a function is a solution of a differential equation, and we can even try to find a solution of some type. That's relatively easy to check. I think that I would like to stop here. This is it for this video.